Hi, my name is Kevin Keefe, and I'm a fifth-year PhD student in physics. Before I was a PhD student here at UH-Manoa, I earned my bachelor's in science and physics and my master's in education, both from the University of Florida. For a few years afterwards, I was a high school teacher and an adjunct professor where I taught different science courses, both in a high school and a university setting. The courses I taught included earth space science, chemistry, physics, and astronomy. And that experience I gained as a teacher only increased my passion about education. And this experience eventually led me back to continue my own education and pursue my own research interests as a PhD student in physics. I began my work here as a research assistant at the end of my first year at UH with Curtis Nishimura, and I worked on the development and characterization of a portable neutron imager. This was my first introduction to digital design, as well as scalable electronic solutions to high energy physics problems. Between my third and fourth years, I worked as an intern at San Diego National Labs, where I continued my work on a second design prototype of a neutron imager. This most recent year, I have transitioned to work on a different, albeit slightly similar, high energy physics prototype being designed for use at DUNE, which stands for the Deep Underground Neutrino Experiment at the FAR detector. The collaboration I work with now is called QPIX, and this stands for short for charge pixel. And we are working on the development of a novel pixelated charge readout technique, which we hope to implement in the future at the DUNE FAR detector. One of my interests in this research is the novel use of modern electronics, namely low power FPGAs, silicon photomultipliers, and scintillators. And these modern electronics provide a means of scaling physics experiments, which is crucial for high energy physics, or HEP. My current work within QPIX involves the development and characterization of a digital prototype board, which tests the readout capabilities of several dozen pixels of charge readout. And one of the main challenges of large high energy physics experiments is just the sheer scale of both detectors and the data required to make statistically significant measurements. DUNE and QPIX are no exception. And for QPIX to be a viable design, we have to show that our prototype design not only works, but it can also be scaled to millions of channels and has to be stable at liquid argon temperatures, as well as robust and reliable enough to last for several years of operation. Eventually, with my research, I plan to show that the prototype of the digital design side of the detector can scale, and also possibly show that machine learning algorithms can accurately identify events produced from Monte Carlo simulated events, which are based on the characterization of this first prototype. These improved readouts for the DUNE FAR detector could be useful for discovering new physics. Finally, thanks for listening and for the opportunity to be an ARCS scholar.